The last part of this unit will be on human inheritance patterns. And basically, we're going to learn how to determine the inheritance pattern when given a pedigree. So pedigrees have been used to figure out how is this trait passed from one generation to the next. Which chromosome is it located on? Is it dominant or is it recessive? Those are kind of the questions that we are going to have. Now, this is a pedigree. This is a sample pedigree. And just as we're looking at a pedigree, this is a family. And we start at the top. We have two parents, Jim and Sally. So notice that boys are squares, or males are squares. Girls are circles, or female. And we connect them. That means that they had children together. Maybe not married, but most of the time that means you got married to have children. So we'll just say married. So Jim and Sally had 3 children according to this pedigree. They had one boy, one girl named Linda, and another boy over here. So 2 parents, 3 children. Now, when you look at the children, this boy is not showing to have more children, did not have children, did not get married, something. It's just still just there. But Linda married Bob. The way I know that is because there's a line connecting them. And then the line down connects them to their 3 children, which includes Larry and then 2 other girls. And over here, we have that last son. He got married and had 2 boys. So that's how you follow the flow of a pedigree. That's what all the little bars and lines mean. Now, when we talk about pedigrees, we're going to ask you to identify different individuals on this big family tree. And the way we do it is by generations and by individual. So this should have a little dash. So I thought I'd add that. But the way the individuals are marked is first by the generation. So we use Roman numerals to mark the generation. So generation 1 is Roman numeral I, right? The second generation, II. The third generation, I. 3 I's. And then IV, right, which stands for 4 in Roman numerals. So first, second, third, fourth generation. Then we always number from left to right, just the way we read in English. So 1, 2, and then the next generation, start again. 1, 2, 3, 4, 5, 6, like all the way across. Next generation, you're starting at 1 to the left and numbering all the way over to the right. So this male right here is individual 2, II-1. Or this individual, this girl right here, is individual IV or 4-9. So that's something to note when we start doing problems in work. So I wanted to show you Queen Victoria's family pedigree for hemophilia. I mentioned this before when we talked about sex-linked genes and how Tsar Nicholas's family, of course, they were all killed during the Russian Revolution. So Alexis down here had hemophilia. His mother, Alexandra, was Queen Victoria's granddaughter. Her mother was Alice. So Queen Victoria is a carrier. Her husband, Prince Albert, did not have hemophilia. But you could see her first line of kids, she had a son who had hemophilia. She had 2 girls who carried the trait. And then you can see, if you're looking at the family tree, look at all the boys who have it. And we don't really see even a female who has hemophilia. We really only see the boys. And that's how we figured out hemophilia was sex-linked. was simply by looking at these family trees with all these boys having it and not the girls. So I thought I would show you that. It's kind of cool. And maybe you know some of these names from European history. But for us, we've been talking about genetics, and we've been talking about how you can inherit genetics and what are the different ways to inherit a trait. And so we're going to focus in on 3 different ways to inherit a trait. First, we know you can inherit a trait because it's on the X chromosome, so it's sex-linked. And we've been talking about it, it's always recessive. So you get the recessive trait, then you have it, right? So it's sex-linked and recessive. Now, another way would be that the trait is not on the X, but is actually on one of the other chromosomes that we have, on one of the autosomes. So if it's on one of the autosomes, then we're just going to be talking about, is it recessive or dominant? So are we going to have, if we're recessive, we have it, or if we're dominant, we have it. So these are the 3 types of inheritance of traits that we are going to have a choice of. And I have included just kind of an example of what a typical sex-linked or X-linked, some say X, recessive pedigree looks like. What you see, again, you see more boys than girls. Autosomal recessive, same number of boys and girls usually. It still could be more boys than girls, but. And then also autosomal recessive is like you don't see it very often. It shows up once in a while. Dominant trait, then you usually see the dominant, like more in the family have it all together, and it should be kind of equal, boys and girls. So that's kind of the picture we're looking for. So how do you solve a pedigree? Different teachers have different ways. And you probably know that there's 2 other bio teachers at Valhalla, Mr. Halverson and Mr. Gappy. Mr. Halverson, who teaches AP Bio, he says you should do this. You should first start with sex-linked and recessive, and you should label the whole pedigree like it's sex-linked and recessive in pencil. Then you go and see if it makes sense, like if it can happen that way. And if you can prove it wrong, then you erase and you move on to the next one. So if you find even one example that doesn't work for number 1, then it's wrong, and then you have to erase and start over, and then you do autosomal and recessive, and you label them all, and you check to see if it's right. And if it all checks, you're done and correct. But if you even find one example that it doesn't work, then you have to erase and start over. Then you do autosomal dominant. So notice this is the order. You always check sex-linked, then autosomal recessive, then autosomal dominant. Mr. Halverson's way. Now, Mr. Gappy has a little cheat sheet for you. That's what I call this. So we call it in school, cheat sheet. So he has a little bit of a check to see if any of these are true. And then if they are true, then go ahead and use pencil and fill it out. If you find if any of these are wrong, then you can just skip this one and and check for the next one, right? Autosomal recessive. And then you check these. And if these are all true, then you go ahead and fill out your pedigree in pencil, and usually you're right. And if any of these are not true, then you don't even have to fill it out, and you just move on to the next one. So there's 2 ways of doing it. I am going to show you Mr. Gappy's way because I kind of like it. It's less erasing. But, of course, you can always do Mr. Halverson's way. So we'll start with sample problem number 1. So we're going to do some problems. This is in your notes. And so you want to have this handy because I'll be referring to it. So we're going to start with sample problem number 1. If we go by this chart, we're going to start with sex-linked and recessive. So we're going to look and we're going to see if a female has the trait, then all of her sons will have the trait. So let's just look. So we're looking for a female who has the trait, and then do all of her sons have the trait? This one is a yes, and here's the female with the trait, and both sons have it. So basically, that's a yes. Keep going. Next one on this list. If a female has a trait, then her dad must also have the trait. So this female has the trait, and if you look up, so does her dad. Now, what about this female? Well, we don't know her dad, but we do have one, so that's also a yes. So far, we have not proven otherwise. Next one, if both parents do not have the trait, so they look like this, then they can have a boy who has it and a girl that doesn't have it. So a girl cannot have it if both parents do not have it. All right, so we don't have that example up here, right? There is no both parents not having the trait. So this is like a NA. It's not a yes or a no because we don't have that example. So then we move on to the next one. If both parents have the trait, so this and this, then all of their children will have the trait. So both parents have the trait. All of their children, no. So we found a no. This is a no. If this is a no, we move on. So it's not sex-linked and recessive. So now we try autosomal and recessive. So if we try autosomal and recessive, it says if both parents do not have the trait, again like this, they can have children with the trait. So we have both parents who have the trait, and they do have a mix. So that's okay. So that's kind of a yes, it works. If both parents have the trait, then all of their children have the trait. Both parents have the trait, but not all children have the trait. So it's not autosomal recessive. So that's a no. So we already clicked off no and no. Last one. Autosomal dominant. We're pretty much going to go ahead and start penciling it in because we think it's going to be correct, right? So now let's look at the labels. Everyone that is circled dark in, they have the dominant characteristic. So that's what I usually just kind of hone in like one at a time or my brain gets confused. So this one that is filled in has a capital A. So I find all of them that are filled in has a capital A. Now, if I look back on this, if they do not have anything filled in, it's lowercase a. So that would be little a. So this is how I fill out all of them. This is how I start. Now you have to understand genetics, which I hope by now you know that this parent is either going to give this little a or this little a. This parent is going to give this a or something else, whatever they have, to their child. So kind of work, a lot of times I work backwards. So if this child is little a, and they got one of them from this parent, they did not get both. They cannot do that. They only got one. So what would this parent have to have? This parent would have to have a little a. That's the only way you get this child. How about here? Well, this child has a capital A, got that one. What did they get from this parent? Oh, they would have had to get a lowercase a. Now I'm going to skip the husband here and scoot over to the other child. Already done. All right, so we're kind of done there because usually I look down at the next generation. So now I have this set up where I know this is a capital, this is a capital. I know they have the lowercase because of the parent. Now what about down here? So these two children have lowercase a. They got one from this parent. So what do they get from this parent? A lowercase a. Now, this parent could have given this letter. This parent could have given this letter. So I have no idea what the other letter of this child is. Because it could be big A, or it could be big A, little a. So I don't know. So when we don't know, we just put a little dash. We have no proof one way or the other. How about here? Well, this parent is going to donate a lowercase a. So both of them are going to have that. But what about this parent? Wouldn't really know, right? We don't know their parents. And this A definitely could go to either one. They could have two capital A's, or they could have a lowercase a. So this parent, we don't know either. And so that is the proper answer. This is for sample problem 1. In sample problem 1, we decided that this was autosomal and dominant. So you'll be filling this out, and then I will be asking you problems on the worksheet. On your practice will be, so this is not labeled, but I can easily label these. And you can do it too. It's not rocket science, right? But so then I could say, what is the genotype of individual 2, 3? And then you would tell me capital A, lowercase a. What is the genotype of individual 2, 5? And you would tell me capital A dash. Don't know. How many individuals on this problem have the characteristic? That's asking you to count the shaded boxes. 1, 2, 3, 4, 5, 6, 7. So how many? Count. How many are homozygous recessive? Count. 1, 2, 3, 4, 5. So I could be asking you the genotype of an individual. I could ask you how many there are. Those types of questions will be what I ask you on the practice. So the first step will be to identify what kind it is, to then write out all the genotypes, then answer questions. So let's try sample problem number 2. Here we are, sample problem number 2. What is the inheritance pattern? Label all the genotypes. So again, we're going to start sex-linked and recessive. We have to prove it wrong before we get to move on. If a female has a trait, then all of her sons have the trait. Female has it, all her sons have it. Okay, we're good. A female has the trait, then her dad must also have the trait. Female has it, we don't know her dad. Female has it, the dad does have it. Oh, okay. That's a yes, right? If both parents do not have it, that's not a choice, so we'll skip that one. If both parents have it, well, that's not a choice. And only females can be carriers. That just means that you can have children and the female doesn't have it. But that one's kind of hard. I kind of skipped that one. So for me, we have not said no. It's still not 100% sure it's sex-linked, but we haven't said no on the little cheat sheet. So since we haven't said no, we're going to go ahead and try it. And that's what pencil is for, because we still could be wrong and we might still have to erase. But if we start filling this out, again, looking at our labeling, a girl who has it is X little a, X little a. So we'll go ahead, we can fill out that. So there's the girls. Again, I usually just try to focus one at a time. It helps me keep it apart. Okay. If a boy has it, X little a, Y. So this is really when it counts for the boys and the girls, right? Okay. If the girl does not have it, X capital A, X blank. Okay. So X capital A, X blank. And then the boy that doesn't have it, X capital A, Y. All right. Now we have a couple of blanks, right? We have this blank, and this blank. The question would be, can we solve this blank before we let it go? So can we figure out what this mom has based off the children? So the boys got a Y from their dad. That's the only way they're a boy. So it doesn't even matter what the dad has because boys get just Y. So the other one comes from mom. So far, yeah, the mom has a capital A, we know, because that's why she has boys who don't have it. We can't really tell what this other one is. And even here, if we're looking up, don't know. Well, actually, I take that back. See, this is when I'm thinking without recording. The girl got an X from the mom, and the other X has to come from the dad. Because the dad didn't give the girl the Y. That's why she's a girl. So we do know this one. Because her dad has the trait, we know she has to be a carrier. All right. Then down here, dad has it, so does the girl. So we know she's a carrier. So the only one we don't know is this mom, and it's because we don't know her dad. That's really why we can't tell for this mom up here. But we can tell for the daughters down below. So that is now complete. So we have one that we don't know. The rest of them we know. And again, I might be asking you how many boys have it, how many girls have it. What is the genotype of this individual? So those are the types of questions we'll be asking after you complete this part. So once again, this is the answer. And we did decide it is sex-linked and it worked. So had we filled this out and then we had noticed that these two parents can't have this, then we would have had to go back and figure out what was wrong. So we could still have found it to be no, but sex-linked is the answer for sample problem number 2. Okay? Sample problem number 3. Back to this page, starting at the beginning again. And that's the part where it's like again. All right, if a female has the trait, then all of her sons will have the trait. Female has it, all of her sons have it. Okay. If the female has a trait, then her dad must have the trait. So do I have a female has the trait? Her dad has the trait? No. So I already found a no. Since I found a no, it's not sex-linked. Next one, autosomal and recessive. If both parents do not have the trait, do we have that? Okay, here. Then they can have boys and girls that have the trait. They can have. So they don't have the trait, but they can have children that have it. Okay, that kind of works. Both parents have the trait. All of them have the trait. No, that's not a choice. And then females and males can be carriers, which hard to tell here if a female is a carrier. So I can't say no, which means I'm going to try this one. I might be wrong, but I'm going to go ahead and try it. And then again, I'm going to fill it out the way it says. So this is opposite of the dominant, right? So we're looking here. If they have the trait, they're going to be homozygous recessive. So I'm going to look at it, find all the ones that have the trait, and I'm writing homozygous recessive. Then, if they don't have the trait, then they're capital A something. So that's kind of step one once we've decided. Then we start looking at the parents and the children, and does it work? Does it match? And can we figure out what another parent would be? So again, here we have two A's. One came from this parent, so the other one had to come from that parent. Down here, two A's. The only way this child has two A's is if the parents are heterozygous, right? One came from one parent, one came from the other parent. So now this parent that's heterozygous could have given this one, or this one, this one, or this one. So we know they got a capital A, but it could be another capital A or a lowercase. So we cannot determine this one. We're going to have to leave that one the way it is. We don't know. And then we have this set. This parent is only giving a lowercase a, so the children have to have that. What about the mom? Don't know. Mom could be homozygous dominant and still would have this story. Or mom could be heterozygous and we would still have this. So we don't know that one and we don't know that one. So we have two, don't know. So now we've completed it. It does match. It does make sense. I don't have a child that I can't explain genetically this way. So this inheritance pattern is autosomal and recessive. And again, then I'm going to ask you about the genotypes. Who has the trait? Who doesn't have the trait? What is their genotype? Which ones can you tell? Which ones do you not know about? Any sort of questions like that. Now, I know I made this into 3 different pages. So let's see if I can find my one that you can see completely filled out. And I will zoom out for you. And you can kind of get an idea of your completed notes page. So a little hard to get to focus. But that is your completed notes page for